So this is a follow-up to my prior video where I summarized some of the challenges with our field installations that use inexpensive water sensors for flow detection. To recap, I summarized the build of a new float sensor and improved DC barrel jack connection that will hopefully diminish maintenance challenges moving forward. In this video, I'll summarize the field installation of both a vertical float sensor coupled with a conductivity sensor that's talking to a 4G remote environmental monitor, and I'll also share details about a horizontal float sensor that we'll be testing at a second site served by a satellite remote environmental monitor. So up to this point, I've briefly summarized a simple build for a float sensor that is fully encased in plastic and thus more resistant to corrosion, typical of acid drainage in the mining districts my agency monitors. Since the enclosure hosting the float fills from the bottom, I'm also hopeful this will be better suited to withstand impacts from sediment. Having said that, one of the challenges with float sensors is that not only can they become impacted by sediment, but as one of my colleagues pointed out, the magnet embedded in the float can attract magnetite suspended in stormwater. That in turn can cause me to miss my stormwater event and I'm back at square one. In response, it occurred to me that maybe I could just back up or even replace the float sensor altogether with a simple conductivity sensor created off the DC barrel jack pigtail. To see if this would work, I tested this idea out with both some distilled and tap water, as I'll demonstrate over the next few seconds. So briefly, here's the test with distilled water off those pigtails. You can see that I'm not getting a red light on my microcontroller as I did with the float sensor, but if I use tap water, which has higher dissolved solids, I do get that red light. So certainly conductivity can work as long as you have enough dissolved solids in your stormwater sample. So here you can see that I've got my float sensor and my conductivity sensor both basically sharing the same ground and anode for detecting flows in my stream. This setup will give me an opportunity to test both of these sensors out in the field. Let's see how the float holds up to sediment and magnetite, and let's also see how that conductivity sensor holds up to corrosion. And the other nice thing about this setup is I can replace either one of these sensors very easily with those watertight fittings or those watertight connectors where all I have to do is unscrew the connector, pull the sensor out, replace it with a new one, and I'm done. All right, well here's the boron LTE modem in the field next to our auto sampler. It's running independently for flow detection, so the REM is no longer triggering the auto sampler. I think this is easier for staff to not have to deal with resetting the REM and making sure that it's working well with the auto sampler. In any event, when we first set this up, before we tied it to the tree, we tested reception. And we had coverage out here. I was getting the breathing blue cyan light on the modem, but it's not working right now. Regardless, I'm just going to leave it alone. We've already gone through the trouble of installing everything. You can see that we have our wire headed down to the float in the stream down there, and I'll take a walk down there and show you what we did in a second. And just to follow up on that connectivity issue that we were having, when we installed it, it was running fine, and the Adafruit IO dashboard shows that we did collect data for about an hour before it halted. Subsequently, what I did was log into the Particle IO dashboard, and they've got this really nice interface that lets you check up on the device that you're working with, and you can see here that the cellular strength where we're working is just not that great. So reporting off this sensor and this remote environmental monitor might be intermittent the way it's currently set up. So it's something we're going to have to revisit moving forward. All right, and here's the float over our sampler inlet tubing. And we were a little short on time, so we worked with zip ties to get this thing anchored. And it is pretty sturdy on there. It's not going anywhere. But those zip ties are going to rot in the sun over time, so I'm going to have to come up with a better design. But you can see that our cable follows the sampler tubing cable. It's been wrapped in conduit. It's got zip ties all along.
We've got two sensors on this. As you can see from these two, you can see these two watertight barrel jacks. One is going to the float, and there's another one going to a conductivity sensor that's embedded in this PVC right here. So I'll try to show you the conductivity sensor. Let's see if I can get it in the camera. It's right in there. And I've angled this slightly downwards so that if I get any rain, it doesn't enter that PVC and trigger that conductivity sensor by accident. But that's basically what we've got. Here's the sampler inlet tubing, so it's lower than the sensors. So if the sensors fire and they notify us, chances are good that the auto sampler fired independently and took samples. So there you have it. Let's see what happens. And this is just to give you an idea of what this area looks like, looking upstream and looking downstream. So what we're trying to do is catch a sample through that sampler inlet. There's the auto sampler. The auto sampler is running off of its own sensor, which is that one right there. But I've got this one hooked up to the REM and this one to notify us when there's been flow, so that we don't make wasted trips out here to service that auto sampler. We only come out when we need to.
And the next few seconds just basically summarize a different design for a float sensor that I'm experimenting with right now. Just a quick reminder here that we're also interested in improving our sensor connections in the field. And towards this end, we're trying out these DC barrel jack connections, which the manufacturer claims are waterproof. In this build, our next step is soldering the same to the float sensor.
Okay folks, so I've returned to Alum Gulch. This is the setup that I was at back in July. We're in October now. I can see a little water sensor that was set up by one of my colleagues, which is that little piece of PVC right there. And then this is the inlet tubing for the auto sampler. So it's got some elevation over the tubing, which is a good thing. Now I just got to figure out how to wire up the REM with my new sensor, since this sensor is talking directly to the auto sampler, and we want to try to keep things independent this go around. We don't want to have the REM trigger the auto sampler. We're just going to see how this works independent. Okay, my colleague did me the favor of leaving the cable that's attached to the remote environmental monitor intact. And this is the one that's going to the auto sampler. So I should be able to tie into this cable as soon as I figure out the colors for these leads and what goes to what. All right, and rather than mess around with the colors that were coming off this wire and trying to figure out what was what, I just cut it back. I can see this is going to be my ground, because this is going to help with the shielding on the shielded wire. I'll use that for my anode, and this signal wire I won't be using. The signal wire, because I've only got an open-close switch. So I'll have to figure out something with respect to the REM, how I get that signal wire incorporated in that part of the box. To be determined. All right, so I went ahead and I used this little portable soldering iron to hook up these two leads to the red and the bare wire on the lead going to the REM box, on the cable going to the REM box. For a reminder for next time, I really do need to bring some helping hands out here to help with the soldering, because it's kind of hard to do unless you have something to anchor those wires together. Okay, and as you can see here, the shrink wrap's been applied. The other thing I forgot was a lighter. Lighter would help. I use the heat off this little portable soldering gun to get that to shrink, but it makes a lot more sense to bring a lighter to shrink that. And there's the new waterproof connection. It's just a DC lead that's going to make maintenance of these installations go a lot smoother in the future. You can see it's coming out of the PVC and then just moving straight up to the remote environmental monitor. All right, so next I'm going to go up to the remote environmental monitor, and I'm going to see what the inside of this box looks like and what I need to do to make it work with this new sensor. Also want to make sure I don't have a short with respect to that soldering job and shoving everything inside that PVC. So we'll check that next.
For context on the next few seconds of the recording, what I'll be explaining is my approach for testing the sensor that is now installed in the channel and wired up to my remote environmental monitor on the bank. To be clear, the orange and red leads attached to this little DuPont header are also attached to my water sensor in the channel via this cable that's run up from the channel to this box. Here you can see that the header attached to that cable from the channel has been removed from the proto board and is hanging off screen. Over the next few seconds, I'll explain how I did a continuity test with my multimeter attached to that header. If I have everything wired correctly with no shorts, when I engage the water sensor, my multimeter should realize a high-pitched sound.
Folks, so what I did was I hooked up my continuity meter to the two leads that were plugged into that proto board that I believed were the cathode and anode for the switch. Then I went down to the wash and I engaged the sensor, and I could hear my continuity meter buzzing. So that tells me that I've got everything wired up correctly here. Or at least I know which leads are the cathode and the anode coming from the switch. All right, so what I need to do now that I've plugged in that little DuPont header into the proto board is just figure out which one is my signal wire, which is going to be that blue wire right there. And I think if I short it relative to that red or orange lead, that should do it, because I can see that my interrupt pin number 3, is already pulled low. So that's good. So now all I need to do is short the switch, or short that interrupt pin on the switch, and it should be good to go. So I think I'm going to have to do a little soldering to make that work. All right, so I had a lot of trouble trying to get my little soldering iron in there. It was just too big. The tip was too big to do that kind of work, especially since I'm standing on a rocky slope. So what I did was, rather than trying to solder it on the proto board, I just shorted the leads right off of the little DuPont header. So hopefully this will work. We'll find out. Okay, and since I have a blob of solder that's shorting those two leads on that header, I wasn't sure if it was fully plugged in and making contact with the proto board. So what I've done is I've taken a lead off the multimeter onto the ground wire, and I've taken another lead and I put it on the pull down resistor, and I am getting continuity, which means that plug is in far enough. So that's about all I can do on this. I can't actually check to ensure that this is working with the field test by triggering the sensor, because my cell phone doesn't have reception down here. So I can only get this set up as good as possible, trigger it, and then see how things look on ThinkSpeak when I get back to the office. Okay, so the box is closed. I'm going to make sure that that this wire is securely anchored under some rocks to make sure it doesn't get pulled, so that it doesn't pull that little header out from the proto board. but this is the best I can do with what I've got at this moment. So coming back into the channel, I have a little horizontal float sensor in that big PVC housing. So I just need to figure out a way to anchor this, get the elevation of that float sensor a little better relative to the sampler tubing, and just make this a little bit more field worthy. All right, so Jessica went to the truck to grab some wraparound conduit to protect that one piece of exposed wire right there. I'm hoping that that will hold up to the elements, but this system might be a little bit easier to service in the future with that DC barrel jack that's waterproof. Shouldn't have so many connection issues, soldering issues in the field, etc. Hopefully this will work. We'll find out in short order. We need some rain, which we haven't had for a few months, but bottom line is I think this will work a little bit better than what we had before.